Okay, we're now ready to look at the rules of probability. So, given an experiment, so we run an experiment, say flip a coin, roll a dice, and it generates the set of all possible outcomes, and we call that set the sample space. So given an experiment, the set of all possible outcomes is called the sample space, and we denote that S. And further, if A is any subset of S, we say A is an event. So every subset of a sample space S is an event. And we can illustrate this with a nice little Venn diagram. So the box here represents our universal set, which in the case of this experiment is our sample space S. And maybe we have an event A here, and then everything that's outside of A is the complement. So notice that A union A complement gives you the entire sample space. A intersect A complement is empty. The complement of the sample space is the empty space. S union the empty space is equal to S, and S intersect the empty set is equal to 0. Empty set. Okay, we're going to use this notation right here, so A with 2 bars on it, to be equal to the cardinality of set A. All right, so if I have, let's look at a quick example really quickly. If my experiment is that I flip 3 coins, then the sample space I get is all heads, 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 tails, heads, tails, heads, tails, heads, heads. And then we repeat the same pattern except with T's instead of H's. So that is our sample space S. The cardinality of S, so the size of S here, is 8. And let's say let A be the event that we flip exactly 2 heads. So then A would consist of, it's a subset of our sample space, HHT, HTH, THH. And we see here that the cardinality of set A is equal to 3. All right. Notice the complement of A, if we wanted to write that down, are all the ones where I don't have exactly 2 H's. So the 3 H's, 3 T's, and the 2. So that's all of them. So again, notice that if I take all of A and union it with all of A complement, I get back the sample space S. All right, another definition. We say 2 events, A and B, are mutually exclusive if their intersection is empty. So the sets are disjoint. Sets A and B are disjoint. But in the words of probability, our subsets of S are events, and our events are mutually exclusive if their intersection is empty. Okay? All right. So now let's come up with our definition. The probability of an event A is the sum of all the weights of elements in A. So we'll certainly see many examples of this. All right, so that's going to be our working definition. We also need, so that we can go on our journey, a set of axioms. So these axioms we accept, and from them we prove many more things. The first of which is this probability, how we're going to define it, of the sample space is equal to 1. And the probability of the empty space set is equal to 0. The second thing that we're going to require is that the probability of any event A is between 0 and 1. And the third one is if the intersection of A and B is empty, that is, they are mutually exclusive, then the probability of the union of those two sets is just the sum of their respective probabilities. Okay? Perfect. Now, what we can show from those axioms, many things. One of which is that the probability of A is equal to 1 minus the probability of its complement, and vice versa, right? And the probability of A complement is equal to 1 minus the probability of A. Let's do a quick proof of that. All right, so one thing we know, so probability of S, the probability of S is equal to the probability of A union A complement, right? Because A union A complement is S. We know that A and so this is equal to, this is by axiom 3 right here. That's axiom 3. And we know that that this union equals the sum because A and its complement are intersection is empty. And axiom 1, that's axiom 1 right there, right? The probability of S is equal to 1. So 1 is equal to P of A plus P of A complement. So I just solve for one or the other, and I get 1 minus this. This is a very useful tool for us. Sometimes finding the probability of an event, it's easier to find the probability of its complement. Okay? Now, a recurring tool that we'll use in here is where we take a set and another set, and we split it up into a union of disjoint sets. And let me just explain what I mean here. So let's say we have A and B here. This stuff that I'm shading right here is A and not B. So A intersect the complement of B. And then the stuff right here is A intersect B. And if I want to take the union of those, do the union of those, notice that I get all of A. So A is the union of these two sets which are disjoint. All right, so that is going to be a very common tool that we use. We'll stop there.